Okay, so good afternoon, good morning. So now we continue, but first you open the SPSS, yeah, now, yeah.
Sorry, sir. Regarding the question just now, are we able to write down the function 1, function 2? Means write down all the functions like regression analysis kind of function.
No, okay, no. Basically, it's the idea. The idea. Okay, it's the idea.
Thank you, sir.
Okay.
So then, can we get the weightage?
No.
No, also.
No, it's okay, no.
So we just get the which are the most discriminants by which indicator?
Again?
I mean, so which variable that we can decide to be the most having the most discriminating power?
Of course, the one from the equality lah, equality.
I mean,
We are going to see also the potency index. Yeah. I think should be today lah. Should be today. Yeah.
or potency index.
Yeah.
Okay, thank you.
Okay. Okay, so again, attendance, I will mark today 3 sections. Just now done, and then next will be third and fourth. Okay. Second thing, I think some students send me the data and don't get checked. I'm sorry, but I will try to reply tomorrow. Okay, tomorrow. Yeah. Okay. So. Okay. I think got few, 2 or 3, and don't get reply. Okay. Some reply, but I think 2 or 3 don't get reply. Okay. So we see. Okay, 31 okay, we can start now. Yeah, okay. So, okay, any other question for the previous discussion, okay, before we start the new section? Yeah. Okay, so if not, now we see we find the output first, yeah, then go to the slide, okay, we do it now, yeah. Okay, so analyze, classify, yeah, discriminant. So we still use the same model like just now, okay. So means it's the income, 1 until 4, maybe can be a bit faster, yeah. In the second time, we do the same thing in the same day, yeah, okay. So 5 until 11, okay, altogether 7, okay, 7 independent variables, okay. 36, we want the mean univariate ANOVA, okay.
Sir, sir, cannot see the screen yet.
Oh, okay, I'm sorry. Okay, yeah, thank you. Yeah, thank you. So now I'm sharing the screen. Okay, yeah, thank you. Okay, so okay, so now okay, it's okay. Don't worry. I repeat, but it's the same thing lah. Okay, so I still repeat. Don't worry. Okay, classify, and then discriminant. Okay, so and then the income. Yeah. Okay, the income. Define range 1 until 4. Continue. Okay, the independent 5 until 11. Okay, 5 until 11. Okay, so use the enter independence together means it's the enter. It's like the enter method here under the multiple linear regression. They're not the stepwise. Okay. So, okay, 36. Mean. Okay. Remember univariate. Univariate ANOVA actually is the one that for us to find each variable significant. Remember this thing? Okay. So where the p-value is less than 0.01, so we take it. Means the one with the have the higher discriminatory power. Okay. Okay, post M. Okay, and then Fisher. Okay. So okay, this one done. for the 36. Okay, classified, we want the compute from the group sizes because group size can be different. Yeah, we did not assume they're the same. Okay, so and then the summary table. Yeah, okay, leave one out classification and then replace. No, this one no need because no missing value. Okay, okay.
So what is the leave one out classification?
This one, later we see. Later we see. Okay.
Okay.
So and then combine. Okay. Okay, and then we can also this one done. Okay. Okay, and then save. So this one we save the discriminant score. Okay. Okay. Okay, done. Okay, so continue. So this okay. Yeah, this is the output. Yeah. Okay, so we discussed a little bit just now. Now we can see a bit more detail. Okay. Okay. So we see we are based on the slide we are going to see more. Okay. So okay. Okay. So now we done already for calculating the discriminant score for each observation. Okay, so we have the three functions. Therefore, here got three columns. Yeah. So these are the okay. So this one okay, this one. So these are the discriminant score. Okay, discriminant Z score. Okay, for each function. Yeah, for each variable. Okay. Sorry, for each function, for each observation. Okay, for each observation. Okay, it's a Z score. Okay, so this one done. Yeah, okay. This is first later we are going to use this to what do you call? Later we are going to use this to see the observation should belong to which category, which group. Okay, got 4 groups. Okay. Okay. So evaluating the group differences on the discriminant Z score. Okay, and the group different means you will see the groups centroid. Okay. Okay. So we see we compute the cut-off point in the shower. Okay. So this one is the hit ratio. Okay. Hit ratio later we see a bit more detail. Okay. We see this one. Okay. It's okay. Okay, so means we got one part to discuss the cutting score determination, how to do calculation. Okay, for the cutting point, cutting score determination, and also the classification matrix, and also the classification accuracy. Yeah. Okay. So, okay. We'll discuss a bit just now, but it's the idea. Okay, we are not going to get the W1. Okay, also the Z. Okay. So this is the idea on how they actually come up with the 3 functions. Okay, so something that they cannot explain in function 1, they pass to the second function like that. Okay, this one discuss. Okay. 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 So for this one, you actually only follow the original data, yeah, to compute the prior probability. Okay. Okay. Of course, they use this to do the calculation. Yeah. So means we did not assume they are the same. Yeah. We did not assume they have the equal group size. Therefore, it's better. Yeah. So a bit more practical. Okay. So okay. Now calculate the optimum cutting point. Okay, we do this now. Yeah. So we compute the optimum cutting score value, yeah, as a weightage. Yeah. Weightage average based on the assumed sizes of the group and derived from the sample size. Okay. So we see this case. This is not our case. Here, remember they got Z score for 2 different groups, A, B, and this Z score bar actually is the group centroid. Okay, I show you now from the output. Yeah, now, yeah. Okay, so the group centroid. 4 values. Yeah. No, this one, not this one. Wait, yeah. Oh, it's correct. No, this is function. This is function. Okay, wait. Okay. Okay, correct. This is correct. This function on the group centroid. Yeah. So another one is the structural matrix is for us to find the discriminant loading. Therefore, it's correct. Okay, it's here. Okay. So, it's wait. This problem too many. Okay, but no problem. You can find it. It's correct here. Can you see? Okay. So negative 1.441. Okay, the 4 values. Yep. Okay. So, okay. Okay. So of course, let's say you want to find the cutoff point, yeah, between the 1 and 2, the group 1 and 2, means you should use the what they call the group 1 and group 2, negative 1.441 and also negative 0.422, like that. Okay. Okay. So now for us, we actually want to we do this one first, but again, this is not our case because this case is assume the width, the equal sample size, but for us it's different a bit. Okay, so we can see also the group size from here. Group size is different for each group. So can you see 20, 23, 36? Okay, therefore different. Okay, means cannot use this formula. Okay, but in case same, therefore we can use. In case same sample size, so we can use this. Okay. Okay. So it's okay, no problem. I know the formula. So the Z score, the optimum cutting score, yeah, actually is equals to Z A bar plus Z A Z B, Z B bar divided by 2. That's it. Okay, it's easy for the equal sample size. Okay. Okay, any question? Yes. So if now we see what is the meaning. Yeah. Example. Let's say this is the let's say 0.832 example. Okay. Therefore, anyone with the Z score less than 0.832 consider purchaser. Anyone with the value more than that is considered a purchaser, like that. Okay. So you can see here. Therefore, sometimes it may happen some what they call the misclassification. Yeah, it's still possible. Okay. So from here we can also see some example. Yeah, let's say this Mr. M. This example. Okay, Mr. M is for here. So suppose belong to two groups. Can you see? Okay, so looks like belong to two groups. Yeah, can be A, can be B. Yeah, can be A, can be B. But here, based on this cutoff point, it belongs to A. Because anyhow, it must have some criteria for us. Okay, but actually, maybe it's from B, but now put it under A. That means suppose it's purchaser. We assume this is a non-purchaser. Therefore, it's a misclassification. Okay, like that. So this one may happen. Okay, here and also this area. Okay, but let's say the diagram like this means still very good because the predictive accuracy is still very high. Yeah, I think more than 80%. Still considered very good. Okay, so this is for the equal size. Okay, any question? Yes. Okay, so if no, wait, I see the checkbox. Yeah. Okay. Standard error. What do you mean by standard? Standard error for each region. Even this too small area. Are you saying that? What region?
Yep. This region, yeah.
No. We don't have such information, and we cannot make such comparison. Yeah. Because you see these two diagrams, they are all normal. Yeah. You cannot say, no, we cannot say standard error is higher. Not like that. Okay. Yeah.
Because if for on this region, it is like a border between whether they want to buy or not buying, right? So the uncertainty is very high, I guess. Because overlapping.
Not like that. Not like that. Okay. Okay. You can see some. Okay. In general. Okay. In general. Okay. Because human being is like that. Okay. Example. Okay. We say example. Yeah. Not because nothing cannot say standard error. No, cannot. Okay, cannot. Okay. So you see example. Income can be a good group. What do you call? A group variable. Suppose is strong enough, yeah, for us to discriminate what car the person is using. Suppose. Okay, but not always correct. Okay. So example. Yeah, let's say high income. Of course, income is symmetric. Okay. So will affect the car that people are using. Yeah. Okay. Okay, let's say BMW. Okay. This here, let's say make it two groups. Okay, two groups. Okay. Okay. And then Viva. Yeah. Okay. So yeah. Okay. So okay. We can see sometimes. Yeah. I can give you. I mean, many individual example. They earn about 10,000, but they use MyV. Okay, and then for those who are working in bank, you may know that some cases they earn not that high, maybe it's 5,000, but want to buy BMW. I think I read the news. Got one case, I think below about 3,000, but the installment is 1,000 plus to buy the car, something like that. Finally, can afford sell buy the car. Yeah, okay. So this one may happen actually. Meaning that in general, we can use income to see what the car people are using, but not always correct. Can I say?
So this is outlier, I guess.
Outlier.
Can I say so? Or this is a residual? Consider.
Maybe consider residual. Yeah, therefore
Okay.
this will make the result not so good. But this happen. Yeah. Okay. Yeah.
Okay. Okay. Thanks.
Okay. Continue. Yeah. So we see. So we are here. Okay, this one done. Okay. So we see this is more practical for our case. Okay. So we see the problem that we cannot use this formula for unequal sample size. Okay, why cannot? Okay. So we see for the group B, the n is higher. Therefore, you see a curve more data, more observation. B. Okay. The n is higher. The A is n is smaller, small sample size. Okay. Therefore, if you did not use the weightage, yeah, you can get this cutting score because the effect of the group B will be more on the calculation. Okay, the effect of course the B will be more, yeah, in affecting the Z score. Okay, because more observation in B. Okay, so therefore it will be here. Therefore it's not good. Okay, so because if here means looks like the error will be more. Means this area is error. This area also error. Means misclassification cases will be more. Okay, so now but actually the optimum. Let's say the optimum score is good. Means the error should be small. Means the misclassification case will be lesser. Okay, means you should consider the weightage, yeah, the sample size. Okay. Okay. If no problem, now I give you the formula. Actually, formula is available in the textbook. It's okay. I give you now. Yeah. No, okay, like this. Yeah. So Z, Z. Yeah, you can put a symbol. Let's say ZC. Okay, cutting point. Okay, cutting score. Is equals to NA ZB. Yeah, equal plus NB ZA. Yeah, NA plus NB. So N is the sample size. So Z is the Z score. The centroid. Okay, the centroid for B. The centroid for B. For A, like that. Okay. So this is the formula. Okay. Okay, so therefore we consider the weightage, okay, of the what do you call? Consider the weightage, yeah, for each group. Okay. I think this will make a not correct statement. I'm sorry. Okay. Okay. So you see actually like this, yeah, like this, yeah. If we did not consider the if we did not consider the weightage, yeah, actually the group A was dominant. Yeah, can you see the average? Let's say here is 4, here is 8, therefore here will be 6. Okay, therefore actually A dominant, not B. Yeah, therefore average is here. Okay, yeah, but if you consider the sample size, therefore move a bit more to the left, yeah, to the A. Okay, but it's okay. This is a statistical issue. Yeah. Okay. So it means you should consider the weightage if they are unequal sample size. Okay. Yeah. Okay. So if no problem, now we see the next. Yeah. I'm done for the how to compute the optimum cutting score. Okay, for equal sample size or unequal sample size. Okay, so this one done. So now we are here. Okay. So we see now we see the heat ratio. Okay. Okay. So it's okay. This one it's okay. We just see the maximum chance criterion. Yeah. Okay. Okay. So we see this. Then we see the example in the output. Okay. Okay. So group 1, group 2. Yeah. Group 1 actually is purchase. Okay. So group 2 is not purchase. Okay. Okay. So the actual group is 1. We know this. Remember, this is the multiple discriminant analysis. Therefore, we know the group of the what they call the participant. Let's say they are actually the answer they will purchase. Okay, and based on the data analysis, also they fall into this category. Yeah, they're going to purchase. So it's correct. Okay, so it means it's correctly classified. Okay, so would not purchase also match with this. Okay, so therefore these two correctly classified. But there are some cases they are based on data analysis they would not purchase, but finally they purchase. Okay, okay, so like that. This one may happen. Okay, okay, so okay, this is also a misclassification. Yeah, based on data analysis they would purchase. You can see it's predicted based on data analysis. Yeah, but actually they would not purchase. Okay, so therefore we see the calculation, yeah, of the heat ratio. Okay, but before that we see the simple case first for this one. Actual total is 25. Yeah, but correctly classified is 22. Therefore 88%. 22 over 25. Yeah, times 100. 88% correctly classified, yeah, for the wood purchase. Okay, but the non-purchase 20 over 25, yeah, 80. Okay, so this is percentage of correct classification. Yeah, so 88 and 80 for two different groups. Okay, so of course we can also find the total. The total you call it heat ratio. Okay, so this total. Okay, so we sum this 22 plus 20. you get 42. Totally, how many participants? Here, 50. Here, 50. Okay, therefore we get 84%. Okay, this is calculation of the heat ratio. Okay, any question, please? Okay, so if not, now we see.
So
yeah.
just a question. Just
sure.
thinking about the group centroid. Seems like we cannot apply because the group centroid is calculated by SPSS, and then I'm not sure how to apply it. Even though we know the group centroid for function 1, function 2, function 3 for each group, but how are we going to apply it? Yeah, for this one, because seems like
we use this to compute the cutting score.
compute the cutting score.
Yeah, okay, you see this case now? Yeah, no problem, no problem. Okay, discuss already just now. Okay, don't worry, you see this now. Yeah. Oh, no, you discuss yeah, discuss already. Okay. We see example now. Yeah, okay, we see example now. Yeah. So okay, I copy the output. Yeah, okay. 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 It's okay. Use Excel is better. Yeah. Later we also use Excel to compute the potency index. Okay. Today lah, but I don't know which section. Maybe now or next. Or should be next because involve a few steps. Okay. So we see the centroid now. Yeah. I mean how to apply. Okay, we see it now. Yeah. Okay. So here you must consider also the sample size. Okay, we do it now. Yeah. Okay. Yeah. Oh. It's okay. No problem. Okay, we consider also the sample size. Therefore, we see the output to get the sample size for each group. Okay. Okay. So 23, 36. Okay. And two more. Okay, two more. 36 36, 21. Okay, 30. Wait. Sorry, I'm sorry. 21 21, 20. Okay, 21, 20. Okay. Okay. So 21, 20. Okay. Now we see the cut here. Here we should got three values. Your cutoff point here for this. Okay. Yeah. Okay. You see the cutoff point for between group, this is A B, C, D. Okay, easier for us. Okay, group A and group B, we can find the cutoff point. Yeah, so therefore the cutoff point will be, okay, we see the formula. Okay, NA ZB and then NB ZA. Yeah, NA plus NB. Okay. Now, okay. I think I draw a line like this. Okay, I draw a line here, and then NA is 23. Okay, you see the table on the left side. So NA is group A, the sample size for the group A, 23. Okay, multiplied by ZB. ZB will be negative 0.422. Okay, yeah. So and then we plus NB. NB will be 36. Okay, multiplied by ZA. Yeah, ZA. ZA is negative 1.411. 441. Yeah. What's wrong? Oh, okay. Can you use bracket? I'm sorry. Should use times. Not bracket. Yeah. This Excel. Yeah. I'm sorry. Okay. Okay, and then here, NA plus NB, therefore the 23 plus 36. Okay, like that. Okay, so NA plus NB, 23 plus 36. And here, check again, 23 times negative 0.422, 36 times negative 1.44. Yeah, correct. Okay, so the answer will be this one divided by 59. This is the answer. Okay, negative 1 point something. Meaning that, let's say the respondent they have the back Z score below negative 1.04 something, means belongs to the category A. Okay, less than 2000, like that. Okay, that's for this one. Means here, cut off point here for this one here is negative 1.04376. Cutting point, okay, for this. Okay. Okay. It's a maybe you try to do one more exercise lah. Okay. Or no need, up to you. I'm okay. If you want, you can do exercise. Then we can check the answer in a short while. Yeah, up to you. A yes, B no. Wow, very quiet.
So this cutting score should already calculated by the SPSS.
No. You should compute manually.
Manually,
Yeah. Okay, it's correct. Sometimes you should compute manually. I can tell you also one thing. In other software, in other module, also sometimes you compute manually. But do you think difficult this calculation?
No, not difficult.
Yeah.
I'm just thinking. So after we got this cutting score, so that means for a new data set, so we just look at the, let's say we choose function 1. So we calculate the Z score. Then from there, for the new data set, we can decide this is belong to group A, B, C, D.
No, actually no. Yeah, because not easy to do calculation for the Z score. Yeah. If only even for not easy to compute manually. Because Z score you need to have the mean, yeah, for each variable. Yeah, not easy. Yeah, okay. But of course the software will compute the Z score for you. Z score for each function. Yeah, for you.
So let's say we already get the cutoff point is negative 1.04376, and we need to find the Z score for each of the respondent or each of the cases, right? And then compare with this cutoff point.
Good question. Okay, good question. Okay, thank you very much. Okay, I show you one more thing. But it's okay. Okay. We see here. Therefore, it's okay. I show you one more. Yeah. Since you asked, no problem. Okay. Can you see here? Only showing this. Now I remove this. Okay. I remove this, and then I will do something. We will get four columns, 4 more columns. Okay. 3 still the same like just now, but I will show you one more column. Yeah, good question. Yeah, thank you. Okay. So classified discriminant, and then I just add one more thing. Yeah, can you see here? Predicted group membership. Means the software will show us based on that score, this individual supposed belong to each group. Okay, we see this now. Yeah. Okay. So now we have the data already. Wait. Oh yes, correct. Can you see here? Yeah. Okay. So remember, based on the analysis, based on the calculation just now, anyone below, where is it? Okay, here. Okay, anyone below negative 1.04 will put it into the category A. A means 1 lah, kan? Yeah, category 1. Yeah. So below negative 1 point something, 1.0. Yeah. So we see example like this. Can you see? Yeah, negative 2. So category 1. Negative 2, category 1, and so on and so forth. This is already more than, you see, already more than this. Okay, so negative 1.01 is larger. Therefore, fall into the category 2. Okay, this is the how they work.
So
that means the SPSS already helped us to distinguish which group they belong to, so we don't need to calculate manually, right?
Yeah, of course, they actually calculated for us which what they call which individual fall into which category. Yeah, remember we have the diagram also. Yeah. To check the misclassified, of course not too good. This is the diagram. Yeah, because we cannot see too clear. Yeah, but you can see roughly good or not good. Yeah, I mean the classification. Okay, so we also can have this. Can you see here? Yeah. No, not here. One more. The classification index. Not here. One more. Oh, I don't have. How come? Okay, correct here, correct. Okay. So you see the clause, not the original. Okay, the original one. Can you see 14, 22? Yeah, 7. Yeah, this 14 means correctly classified. Okay, 14, 22. Yeah, of course they give you answer already. Yeah, 57%. Can you see? Okay. Yeah, like that. Okay. Okay.
So sir, just now the showing the 1, 2, 3, 4 group, that is considered predicted. This is a predicted, right?
Yes, correct. Predicted. Yes, correct. Correct.
Okay.
Therefore, can be not correct. Example, observation 1. Observation 1. Okay, observation 1 still correct because more than 4,000. Okay. Observation 2 less should be 1, but now the predicted is 2. Therefore, it's not correct. Like that. Can you see? So observation 2 should be less than 2,000. Yeah, this is actual. Yeah, based on the data. Okay. So, but the predicted is the second. Yeah, 2001 to 3000. Therefore, it's not correct. Okay. Yeah, like that. So therefore, this percentage is higher is the better. Can you see just now we say for 57? Of course, we calculated also the similar thing using the example in the slide. Okay. So yeah, this yeah. So here 84%, but in our data it's 57. Yeah. Therefore, of course not too high. So the higher is the better. Yeah, like that. Okay. So the higher means you can make more make better decision. Okay. Yeah. Okay. So example, you want to target, let's say high income. Yeah, high income group. Let's say to offer some holiday package to overseas. Let's say the package is more than 20,000 ringgit. So no point to send the package here to the low income people. Okay, in general, okay, in general, okay. I mean, they may choose other lower price package, but not 20,000 ringgit for one person. Okay, like that. Okay, that's a fact. Okay, that's a fact. Okay, it's like that. Okay. Okay. If no question, now we continue.
Sorry, sir, just now how you turn the number to the variable name?
Okay,
The group name.
this button.
Oh, okay. Thank you, sir.
Okay, yeah. Okay, if no question, now we continue. Yeah. So means this button they turn the of course because we already key in the meaning of 1, 2, 3, 4 in the here. Can you see? Yeah, already key in. Okay, you must do setting first. Okay, it's not simply come like that. You do setting first. Okay. So if no problem, now we continue. We are now in the classification. Already done the hit ratio. Okay. So therefore, okay, so we can link it to the multiple linear regression. The classification matrix and hit ratio actually is similar with R square. Okay, so but R square is more to quantitative, but here it's more to qualitative. I mean, okay, I can say it's more R square is more metric. Yeah, but this is not metric. It's more the counting. Okay, okay, counting. Okay, so therefore you get it's similar with R square. Okay, continue. Okay. you can access the heat ratio both overall and also by group. If did not mention, means what they call is for the overall. Okay, so okay. So here's some sample, some guideline for your study. Yeah, if the estimation and analysis samples both exceed 100 cases, and each group exceed 20 cases. Okay, so means it can consider our case because we have 100 observation 100. Okay, and each group also more than 20. Okay, can you see? Here, can you see? Or more than 20. Okay, still meet the meet the criteria. Okay. Okay. So therefore it's good. Therefore we can derive separate standard for each sample. Okay. So example, some maybe want to above 70%, some maybe below, must be minimum 50% like that. Okay. So if not enough, let's say too small, only 10 observation. Yeah, for each group too small. Therefore, just derive a single standard from the overall sample. Already good enough. Okay. Okay. Any question? Yes. Okay. So we can get the misclassified observation only from this diagram. Okay, discussed already a bit just now. Yeah, I think not going to see these two actually are too technical. We see the diagram. Okay, where is it? It's correct. Okay, like this. Okay, like this. Okay. So to see the overall misclassification. Okay, yeah. Okay. So of course, it's also easy for us to compute the inaccuracy because let's say here is our data is 57%, meaning that inaccuracy will be 43%. Okay, like that. Okay. So if no question, now we see. Wait. Okay, now we see next. Now we see this one assessing the predictive accuracy. There are, I think some are same thing. It's okay. We see now. Yeah. Again.
Oh, sorry, sir. No.
Okay, if nothing, then continue. Yeah. Okay. So there are multiple criteria for comparison of the heat ratio. Okay. So the maximum chance criterion. Okay, we discussed already. Okay, just now. Yeah. Okay. So therefore, a bit as usual. Let's say the overall sample is less than 10, therefore must be very careful. Okay. So or less than 20 also must be careful. Means small sample must be careful. Okay, more is better. Okay. So this one I'm not going to discuss. We see here this minimum okay, 20% and above. You'll consider good. Okay. Of course, I know some company may want more. Okay, they may want more. Yeah. Okay, so we see interpretation of the result. Okay, standardize the discriminant weights. Okay, so here we can see the contribution of each variable. Yeah, okay. The contribution of each variable on the what they call on the function. Okay, on the discriminant. Okay, so I think we don't have this. Okay. Okay, so we don't have this. Okay. So but you do the later you do the potency value. Okay. Okay, so we see the second one. Second one we have this the discriminant. Okay, discriminant loading again is quite similar with the factor loading. Okay. Okay, we can see it from the structure matrix. Okay, we see as we discussed already. Okay, so anyhow still can ask. Yeah, so you see this is correlation. Okay, it's a correlation between between each variable with the correlation between each variable with the function. Okay. Okay. Okay, therefore, of course, again, we see the absolute value. Yeah, the larger is the better. Yeah. Okay. So this one you can see is consistent with the result. You can see product line 7, X7, X9, also X10. Okay. Okay. Okay, actually we have, but it's quite similar thing. Okay, we see this one. This is more important. Okay. 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 So you see, just now, okay, yeah, sorry. Okay, you see anything with the p-value small, less than 0.01, we have the X7, 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 and then X9, 10, okay, 7, 9, 10, they already consider here, can you see? Yeah, correct, this one correct, okay. Can you see 7 is quite high, 9 also quite high, 10 also quite high. Yeah, they handle it in the function 1. Okay, so the important one they handle in function 1. The rest they pass to the second and third, like that. Okay. Okay. Any question is? Okay.
Sir,
Yeah.
the structure matrix table, right? So if it works like factor analysis
Yes, correct.
table,
Similar, very similar.
because, yeah, it's similar. Don't we like cross check whether the variable across 3 function, which one is the highest? Like for this case, we know that function 1 is the only one that has eigenvalue more than 1, right? So we know that function 1 is the one that we're looking at. But if we cross check the values across all 3 functions, there's only one variable in function 1.
There's only one variable in the function 1.
Yeah, I mean, like if you compare the absolute value, the highest, right?
Okay. So we see the taking 0.514, 0.705, 707.
Yes, yes.
Okay.
Yes, yes.
But this one they actually based on the residual. Then they compute the correlation. Therefore, they're not in the same category because we still use the eigenvalue is the largest. Therefore, the function 1. Okay, yeah, like that.
Okay, so
Okay,
this
therefore you
structure
cannot
matrix,
compare the correlation in function 1 and in function 2. It's a bit different. They are different function. Yeah.
so
Okay.
we can interpret as the same as like factor analysis. So
Yeah,
we
yeah.
can't check the cross loading, right?
Yes,
Okay,
correct.
so we're looking at just all the function 1. So we assume the as absolute value. So we know that in function 1 we have x7.524, which is high, and then we have x9.514, and then we have x10.429. This is correlates with the significant value above, right?
It's correct. Correct with the each function. Yeah.
Okay, all right, got it. Thanks.
Okay.
Sorry, sir. Just want to know that the discriminant loading, do we need to meet the criteria as more than 0.5, then we consider it's a good variables to be included in the functions. For example, if I look at x6, or x6 for all the 3 functions is below 0.5.
No need. Yeah. Okay, no need. Okay. Because different purpose. Okay, factor analysis, we want to group them into factor 1, factor 2. But now we are not going to do this. We want to see which factor will contribute more. Okay, which factor will contribute more to the discriminant power. Yeah, like that.
Got it, sir. Thank you.
Okay.
So, sir, can I say that for this multiple discriminant analysis, I would say most of the time we should only the eigenvalue that's more than 1, it may only come only one function, and the rest of function, as you say, is just a residual supporting. Most of the case is like that. Only function 1 is will be chosen.
Okay, good question. So for this case, it's a bit more special because eigenvalue is too high compared to the second and the third function. Yeah, different too much. Therefore, function another 2 not too important. Okay, yeah, like that. Okay, but let's say if they are quite similar, therefore you should also consider the. I mean, let's say 0.8 and then 0.7. Therefore, the second function also quite important. Like that. Okay, depends on the result also. Okay.
Okay.
Yeah.
But if it's a good case, I mean, can we say if we find the case like this, the function one is very outstanding? So can we say we have arrived at a very good case? I'm compared to the case if it's others, we have a lot of eigenvalue more than one, then very close, then will be make our life difficult, right?
But make our life difficult, we still must consider also the second function. Yeah, but still technically we still should consider the second and third function if they are quite similar. Let's say 0.8, 0.7. Yeah, like that. Okay.
Oh, so we should still, there is no any good case or ideal case. It means
But this is considered very good already. But like you say, this case make our life easier. Yeah, because different a lot. 0.3 and 0.054 different too much.
okay.
Okay. Therefore, yeah.
Yeah, life easier means also this is the ideal answer also lah. There's no too much of
Yeah, you can say like that lah. Okay, so you can say like that. Okay, but actually, in terms of the interpretation, we are don't particular too much on this thing. We actually want to see which variable will affect more in the grouping. Which variable have a more discriminant power. Okay, so example, when you want to give the housing loan, what criteria you actually consider? Yeah, of course, maybe income important, their credit score, maybe credit score consider everything. I think the one from banking know better. So, but these are some credit score. They suppose based on credit score, but how they compute credit score can be different for different bank. Example, some bank they consider the past record, the default payment. Yeah, let's say they got some default payment in certain bank, yeah, for how many months, and then record good or not good, their credit limit, everything they may consider. Okay, so either they payment on time or not, or maybe delay 1 or 2 days, all this they consider. Which, okay, like that. Okay, so then they may compare, they may use their current customer. Okay, with their housing loan, how's their payment trend, the payment pattern, and so on and so forth. Yeah, because of course I know the most concerned thing by the bank is that will the customer afford or not to pay back the loan in the next 20 or 30 years, let's say for the housing loan. Okay, so therefore each factor is more important. Yeah, for you to consider. Okay, yeah.
okay. So sir, another question is on this for the unequal group size. So as you in the previous slide saying the two criteria on maximum chance criterion and proportional chance criterion. So we have not passed this yet, right? The maximum chance criterion.
No, it's okay. Discuss already, is it? Discuss already. Yeah, this is the one.
Maximum chance criterion is which one? Sorry, just I want to relate.
This method.
Or this is considered maximum chance
Yes,
criterion.
correct. Yes, correct. Okay, why enough? Because here is equal group size, but now for us it's not.
Yeah.
Okay. Okay, even they are equal group size, but we still can use this method. Use this method already good enough. Okay. Yeah.
Maximum chance means the hit ratio or
Use this one already good enough to compute the hit ratio. Okay. Yeah. Only one method to compute the hit ratio. This is the method. Okay? The rest not too important for us. Yeah.
so proportional chance criterion is we are
It's okay. Enough. Yeah.
no need now. No need go there. Okay.
Yeah, it's okay. No need.
Okay.
Okay. So if no problem, so we see the next. Yeah. Okay. 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 So now we see one more thing is the potency index. But I think maybe after the lunch. Okay. After the lunch. Okay. We see the potency index. They will need. Or I think we need about 20 minutes. It's okay. We do this now, lah. Okay. No problem. We do this now. Okay. Okay. If possible, you also. Okay. It's okay. We do this now. Yeah. You open the Excel also. yeah, okay, you see the calculation, okay, of the potency index. Okay, we do it now. Yeah. Okay. So the potency index means refer to this one lah. Okay, we see how to interpret the result. So higher means is the variable have more discriminant power. Okay. So therefore this method is more. Of course, this one is also can be used. Yeah, but where is it? Yes. It's ANOVA. Not here. Yes, correct. This one. This one we use ANOVA. Therefore, also can be used as the what they call discriminant power. It's good, but we will do potency index, which is much better. Okay. So we do this now. Yeah. Okay. Okay. So now we only consider. I mean, I show you example that we consider also only the function 1, function 2. So in the if you want, you can try to do also function 3, the same method. I mean, I show you the calculation to compute the potency index only using the function 1 and also function 2. Okay. So if you want, you can also do the function 3. Okay. Later. Okay. So now, same method. Okay. Now we see this. Okay. 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 You copy the table to the Excel. You copy, not screenshot. Okay. Because you want the value. Okay. Okay. I think like this. I copy. No. The third function we don't want. Therefore, it's okay. It's maybe easy. It's okay. I see. Like this. So this is the function 1 and then function 2. Okay. Function 2. 2. Okay. So not too difficult, but again, in case cannot follow, you can let me know. I can slow a bit. Okay. So this all remember these values all are discriminant loading. Okay. So they say discriminant loading. We do okay. I do like this. The function 2, I move it to the next part. Yeah, like this. Okay. So now we only do we do first the function 1. Okay. Yeah. Like this. Okay. So step 1, we take the discriminant function, discriminant loading power 2. Okay. Therefore, discriminant loading power 2. Okay. So this is easy for the. Okay. Remove the star. Yeah. Maybe affect the calculation. It's okay. Remove the star. So take this value power 2. Okay. This is step 1. Any question? Yes. Okay. So if no, now we see second step. Okay. So yeah, this one also same thing. I tried many times. We cannot find the button to do the calculation for the potency index. Okay. Therefore, we do it manually. Okay. So step 1 done already. You can call it. You can call it. Maybe it's better. We call it square loading. Okay. Square loading. Yeah. Okay. That's step 1. After that, what we do, we need the relative. Okay, relative eigenvalue. Okay, relative eigenvalue. Okay. So now we see the relative eigenvalue. Now we only consider first and second function. Therefore, okay, yeah. Okay, again depends on how many function we use. Now we only consider two. Yeah. Okay. Eigenvalue for function 1 and then eigenvalue for function 2. Okay. So 1 point. It's okay. 1.3 something. Yeah, 0.04 something, is it? Something like that. Okay, we see the output now. Yeah. Okay. 1.325. Okay. 1.325. Okay. We record first the eigenvalue from the source SPSS output 0.054. Yeah. Okay. If no problem, it's okay. I wait first 10 seconds. Okay, if no problem, now we see next. Okay. Okay. So now we want to find the relative importance of the eigenvalue. We know the answer for eigenvalue function 1 is confirmed must be higher because the calculation is like this. We take 1.325 over 1.325 plus 0.054. This one is the value that we are going to use to compute the potency index here for the first part, here for the function 1. Okay. Okay. So 1.325 plus 0.054. Okay. No. 0. Yeah. Okay. If no question, now we see what value we should use. Yeah, we take 1.325 divided by this number. Okay. So E19, yeah. Okay, like this. Okay. So of course we know the eigenvalue for the first function is much higher. Yeah. Okay, it's much higher. Therefore, this value also higher, much higher. Okay. So if no question, so okay, this is step 2. Any question? Yes. Okay, relative eigenvalue. Yeah. Okay, I give you 5 seconds. Yeah. Okay, 10 seconds. Okay, don't worry, 10 seconds. Okay, so if no problem, now, no, it's okay. Yeah. So now what we do, we compute the potency value. Be careful, it's no, potency value, not index. Okay. If if you have only one function, yeah, therefore you get only this will be the index, only one function. But because we got two functions, we should consider also function 2. Therefore, this will be the potency value. We are going to consider the potency value from the function 2 to compute the potency index. Okay. Yeah. So we see how to, okay. Okay, if no problem, we see how to compute potency value, multiply. Okay. The square loading multiplied by relative eigenvalue. Okay. So 0.25 something here for the product line. Okay, and then we done already this. Okay. So for the function 1, yeah. Any question? Yes. I think I better copy the name of the variable here to the function 2. No, I think not correct. Okay, like this. Yeah. Okay. Okay. Okay, if no question, now we see next. Yeah. So next, we do the same thing for the function 2. It therefore can be a bit faster. Okay, same thing, same thing, until potency value. Then I will show you how to compute the potency index. But now, if you can follow until here, the rest already very simple. Okay, so square loading, square loading. Yeah. Okay. 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 So we see square loading with power 2. Okay, we take the discriminant loading power 2. Okay, remove the star. Okay. This is the square loading. Okay. Any question? Yes. Okay, so if no, now we see next is we want the eigenvalue. The relative eigenvalue. Therefore, it's quite small. Of course, we can just take 1 minus this. Okay, so 1 minus no 1 minus. Okay, therefore we get answer is G19. Okay, G19. Okay, so G19. G19. Okay, yeah. Already for the eigenvalue, yeah, for the second function. Okay, eigenvalue. Okay, for the function 2. Okay, if no question, now we can find the potency value. Okay, for the function 2, multiply. Okay, multiply the square loading multiplied by the eigenvalue. Okay. Okay. So this potency value, you can put the name 1. Okay, potency value 1 and also potency value 2. Okay. Any question is okay. It's okay. As usual, give you 10 seconds. Yeah.
Sir, can you show the relative eigenvalue for function 2 again?
Okay. Okay. So like this. Just because you plus these two numbers must be 1. Okay, I can show you also using the here. Your answer same or different? Okay, don't worry, same answer. If you take this one, divide by this, can you see? Same answer. Okay, 0.03916. Okay, okay, no problem. I show you the working. The working is 0.054 divided by 1.379. Is it same value? This one same. Okay, but for the function 2, you should use the eigenvalue here for the function 2. Okay, so this is 0.03. Yeah, okay, done. Good, thank you. Okay.
So if let's say we have 3 functions, then the denominator we need to put in the third functions, the third eigenvalue for the function 3, right?
Yes, correct.
Thank you, sir.
Okay, so of course, you also must sum out 3 numbers, yeah, including the eigenvalue for the function 3. Yeah, you plus also 0.018 like that. Okay. Okay, so if no question, now we see the final stage. Okay, final stage in the calculation, then we do the interpretation. Okay, now it's a potency index. It's some the potency value 1 and 2. Okay, this is the potency index. Okay, so like this. Okay, so this is more, of course, it's much more better, yeah, compared to the ANOVA. Okay, so of course ANOVA you can find the p value, yeah, but they only compare the what do you call? Yeah, means they didn't consider other factors. Yeah.
Sorry, sir, can you repeat again the potency index?
Okay.
How is the calculation?
Yeah. Okay. Potency value 1 plus potency value 2. Yeah.
Right, thank you, sir.
Okay. Okay. So okay, another 10 seconds for you. Don't worry. Yeah. Sorry. Almost step. Okay. Not yet finished. We do almost step. Oh, this is very simple. Already very simple. Okay. Okay. If no question, now we see this number 1. Kan tak? Ranking number 1 means now you see the highest value. Okay, highest value means they have more discriminatory power. Okay, to see each individual belong to each group. Yeah. So therefore, X7 is highest, 0.26. Okay. So X9 is 2. Okay, 0.25. Okay. Any more? Okay, I think should be 19, is it? Should be 19. Yeah, 3. Okay. So 0.19 and then 0.05. Okay, 4. Okay. Okay, so and then 0.03. No, 0.04 first. Yeah. Okay, and then 0.03, and then 0.006. Okay, the ranking. Okay, so means what? This variable X7 actually contribute the most. Yeah, for us to determine which individual supposed belong to each category. Okay, like that. Okay. Okay. Any question? Yes. This is the potency index. Okay. So okay, if no means
sorry, sir.
yeah.
Can you go back? Just now you mentioned belong to which category? I don't really understand the ranking there. For what purposes?
Okay. So you see, one is X7. Okay. X7. Therefore, when determining the okay, this is for the income group, right? For income group. Okay. So therefore, when you see this one, the complaint resolution, you should roughly know the individual belong to each group. Okay. So we can predict based on this variable. Okay. Example. Okay. You see the mean also. Where is the mean? Okay, here. Okay. Not here. It's correct here. Can you see the X7, the mean is quite small value, yeah, for the low income category, less than 2,000, yeah, 4.5 something. But when it comes to the 4,000, the value is quite high, 6.35 something. Of course, maybe they know how to file a complaint or whatever. But basically, if you know the person give a low rating on this part, you should know the person supposed come from a low income category. But of course, not 100% correct. Not 100% correct. Just like more power. Okay, like that. Okay. Just like you see someone driving BMW, it's a guess, should be from high income, but this is roughly predictive. Can I say? Yeah. So car represent BMW car representing high income, but generally it's correct. Generally, okay, yeah, but not always, okay, not always. So they still may rent the car, okay, it's possible. Of course, no, rent the car also expensive. I know. Okay, I know that. Don't worry. Okay. Maybe rent the BMW car also expensive. Yes. Okay.
So, sir, this is saying that the potency value, it will evaluate all the functions. I mean, regardless of the eigenvalue. So to see that which variable will having the highest power.
Yes, correct. Highest discriminant power. Correct, you are right.
So all functions are regardless how low is the eigenvalue, we need to calculate as all as well. But in this case, the example, we don't take the function tree because just for the sake of
Yes, correct.
yeah.
Correct. Okay.
Then,
So of course, use all the function is the best. Yeah. In terms of calculation, yes, you are right. Yeah, very good. Yeah, you are right. Okay.
and then after we know the ranking, we only take the number 1 because the ranking number 2 is also quite close to 0.226 is 0.25. So how you decide which variable that we can, I mean, up to what ranking, then we have to ignore them.
Not say ignore or what. Of course, we refer to the first few ranking. Yeah, the first few variables. Yeah, means we consider no, here we don't have a specific criteria, yeah, but only the ranking. Means certain criteria that you should consider to see the person belongs to which category, yeah. Okay, so this it means the value higher, more discriminant power. Okay, yeah.
Okay, so we can still decide maybe ranking number 2 and 3 we can still take into consideration, right?
Yes, correct. Yes, correct.
Oh.
But of course, can give you some general guideline also. Example, 1, 2, 3 is good because until 0.19, but 3 and 4 different too much. Can you see? The value is different to a lot. Yeah, therefore maybe consider 1, 2, and 3. Yeah, in practice.
So there's no clear criteria, so we can do our own consideration, right?
Yeah, of course, you should not mention. We should not mention everything. You just mention the first few. Okay, 1 or 2. Okay, yeah.
And the SPSS doesn't calculate potency. We have to do.
I try a few times. Cannot. Maybe the new one. I don't know. Maybe they not get do this. Maybe in the future. Maybe they feel this is too easy. We can do our own. Okay, I'm not sure. Okay, but try a few times. Cannot find the cannot find this. Yeah.
Okay.
So for this function tree, you asking us to do the practice. So the function tree, the Algon's value. So if let's say I want to find the relative Algon's value, I will need to use the Algon value divide by function 1 plus function 2 plus function 3, right?
Yes, correct. Therefore, you cannot use this anymore.
Right.
You see? All right, because okay, you see Algon value 3. 0.0, I think 18, right? Anyone? Okay, you see the output? No, yeah. Okay, correct, 0.018. So therefore, you put in one more value, therefore the derivative value will change. It means cannot be 0.96 anymore. Okay, so total. Yeah. So total these three numbers we get 1.397. Yeah. Therefore the relative eigenvalue will change. Yeah. This one divided by this. Yeah, we get 94 something. Change a bit. Okay. Okay. So therefore you should use. Of course, using Excel is easy. Why not just change the value here? You don't change this one also will change. Okay. Then you add one more area, one more part to compute the potency index 3. Okay. No. You compute potency value 3, and then finally you compute the potency index. Yeah, like that. Okay.
All right. Thank you, sir.
Okay. Yeah. Thank you. Okay. Any question is before we go for lunch? Lunch break. Ask now. Yeah.
Sir? Okay, so because we are comparing based on both function, right, 1 and 2. So if we were to interpret based only on function 1, the potency value, there's nothing wrong with that, since we focus on, okay, we look at eigenvalue more than 1. So I'm only considering function 1. Can I interpret potency value based on just function 1 and regards function 2 and 3?
Okay, good question. Yeah,
Then
this one actually is quite it's a practical question. It's also very subjective. Okay, so depends on the value. Let's say for this case, it's confirm no problem if you only focus on the function 1, because the difference between function 1 to 2 is a lot. Different a lot. But let's say your function 1, 1.3, your function 2, 0.8, means you should consider function 2 also. Okay, see 0.8 still consider a lot. Yeah, quite close to 1. Therefore, should consider function 2 also. Like that. Okay?
Okay.
Therefore,
Right.
yeah.
Thank you, sir.
Like that. Okay. Yeah. Okay. Any question? Yes.
Sorry, yesterday I should have asked this question.
It's okay. That's now. Yeah.
Fully digested yesterday. It's related to the when we want to test the normality of the multivariate. Yesterday you are using the example of using the ID as the dependent variable. So can I say that this is the way we test the normality of the whole multivariate?
Yes.
Because the ID is what we call a random number, so that's how we can test the normality, right?
Actually, not because of that. Yeah. In this case, if you see the guideline, actually, the independent variable is not important. Okay, it's not important. But the method that we used yesterday, Mahanobis, basically is to test the outlier, either the data contain outlier or not. Okay, means if no outlier, is considered normal. In general, this is one of the important criteria. No outlier means normal. Okay, so let's say your data like this is normal, but let's say you got some outlier, therefore they maybe become like this. Can you see? Okay. Means your curve must change a little bit to consider the outlier, therefore no more normal. Yeah. Okay. Like that lah.
So
Okay.
that means a dependent variable we have to choose. I mean only ID, or we can choose other column also. It's on.
I think this use ID lah. This use ID.
Let's use the ID. And for the Mahalanomis, you will explain the concept later.
I think maybe no, because not too important. Only for us to detect. Actually two things. Yeah. Two things. So first thing, Mahanobis, that one is for to detect the outlier. Second is for us to consider to put in the variable or not under the stepwise method. So meaning that the value d power 2, yeah, d power 2 is the measurement, yeah, for the Mahanomis, yeah. So if the value is high, they will consider this first, to the model 1. Model 2, they consider also they add another one, and you see the d power 2 high or not high. High, then they include like that. Okay. Therefore, it's quite, you can assume it's quite similar with the F, yeah, in the stepwise. In the stepwise discriminant analysis, yeah. D power 2 is I'm sorry, Mahanobis, something like this. Okay. Okay. So D power 2 is the measurement for the Mahanobis distance. My pen.
So when d square is high, is normal. It's a normal distribution.
Okay.
When d square is high, that means its distribution is normal.
No, if high means not normal. Depends on the context. This is the measure the distance among the data. Example, let's say they got two usage. Okay, so first thing is the outlier. Okay, outlier. So second thing is for us to use in the multiple discriminant analysis. Okay, for detect the outlier, they compute the distance between the mean from the data. They say some value is very far. The mean here is very far. Therefore, it's not normal.
Yeah,
But let's say
z-score, yeah.
not that score. It's different calculation. They use d power 2, not that score. Okay. Let's say the mean here, the other data is quite close. Can you see? Therefore, it's normal.
Okay.
This is the idea. This is the idea. Okay. So for the multiple discriminant, they compare the group. Let's say group A and B. Okay, and then the variable x1, in these two groups, if different a lot, let's say here 36, here 27, different a lot. For this one, they consider this first to put in to the first model. Okay, and let's say x2, A and B, 7. Here is 8.1. Therefore, x2 cannot help us too much to see the individual belongs to each group. x2 did not help us too much because difference is small. Therefore, the distance, the d power 2 is small in for x2, but the distance for x2 for x1 is a lot, different a lot, 9. Can you see? This is the distance, the difference between yeah. This one, of course, they use the x bar. Of course, they got other things, but in general, they see the x bar. Okay, between A and B, different a lot. Yeah, they put in this first in the modeling, in the stepwise discriminant analysis.
So this square is testing between the group.
Yes, correct. Can you see? It's
So
the same formula,
the
but
higher
they apply in different contexts. Okay, but they can detect outlier. Also can use for us to see which variable should include to the model first, like that.
okay, so they can, okay, so this one is to be different
Yeah, different should be a lot. Only consider the variable is important. Yeah, like that.
Okay.
So means if you are free, you can try to use the stepwise. Okay, stepwise, you change the method in the multiple discriminant. You use the stepwise, then they will show you this d power 2. Okay, then they will show you d power 2. Okay. Anyhow, you can remind me. We can discuss this also after the break. Okay. Yeah.
Okay. Thank you.
Okay. Any question is? Okay. So, okay. If not, now see you at 1:50. Yeah. Okay. 1 hour lunch break. Okay. 1:50. So, okay. We use the same button later. Okay. 150.
Okay. Thank you, sir.
Thank you. Yeah, thank you.